Hi, I'm Professor Angela Rasmussen from the Department of Electrical and Computer Engineering at the University of Utah. I wanted to go over another example of a Thevenin circuit when you have a dependent source in it. So this one is a little bit more complicated than the previous one. Please review the previous Thevenin equivalent with a dependent source to go through the steps on how to do this. So the first step is to find VTH, which is between the A and B. So in this case, it's going to be the same as VO. So we notice that the current source is creating that current going through there. So our VTH or VO is going to be just that 2V2 value, and that's the current times 100. So now we have the unknown of V2. So we locate V2 here. We notice it's going to be this voltage at this wire minus the voltage at this wire. So be careful to not forget to take the voltage difference between those two locations. So if I call this V2A, I notice that this current source is creating current going in this direction. So my V2A is just going to be that current source, and it's going to be opposite the value, which would be plus here to ground in comparison. So this is going to be a minus 4V1 times 100 is going to be my V2A. At this one, that's the same as VTH. So my V2 is going to be V2A minus VTH. And so plugging in those values, I get 400 V1 minus 200 V2. And now I have the same variable, V2, on both sides, so I need to combine them. So I have V2 plus 200 V2 is equal to a minus 400 V1. And so V2 is going to be minus 400 V1. I combine the 200 plus 1 and divide it onto this side for a 201 V1. Now I see that V1 is an unknown variable. So now I want to identify where is V1. V1 is located here. And it doesn't look like there's an easy way to solve for that V1. So I like node voltage, so I'm going to call this node Vx. And then I notice that once I find Vx, I can find the current in that branch, and then I can take V1 from that current. So I'm going to move these over, and then I'm going to draw on the same side so it's easy to see. So my Vx equation in this branch, I'm going to have Vx minus 1 over 10. In this branch, I get a minus 4V1. And then this branch in this way, I'm going to get a plus Vx minus 2 over 10. Equals 0. And now I can combine my V1s, or my Vx's, and I want to also see if I can substitute in V1 in terms of Vx, so that I have one equation with one unknown. So Vx here is going to be the opposite of this current, Vx minus 2 over 10. So erase this. All right, so V1 is going to equal Vx minus 2 over 10. And that current is going in this direction, and V1 is opposite that. So it's going to be a minus times 20. And now I can plug this in for V1 and have one equation with one unknown. So Vx minus 1 over 10. Now a minus and a minus becomes a plus. And I have 4 times 20, so I'm going to call that 80. Vx minus 2 over 10. Plus the last term. And now I'm going to combine all of the Vx's. I have 1 over 10 here, 80 over 10 for the next one, and 1 over 10. And then I have a 110 that comes over from this component. And then I have the minus 2 times 80, and that minus becomes a plus 160 over 10. And then I have this minus 2 over 10 to become a plus 2 over 10. So this becomes 80, this combined becomes 82 over 10. And then this becomes 163 over 10. And then I can multiply by 82 over 10. It actually becomes 1 over that, so this becomes 10 over 82. And the 10's cancel to give me 163 over 82 for my Vx. So now that I have Vx, I can go back and get V1. And my V1 or I'll go back up to this one. So my V1 here becomes a minus Vx, which is 163 over 82, minus 2 over 10 times 20. And multiplying that out, I get approximately V1 is approximately a 0.027 volts. So now that I have that, I can go backwards to get my VO, which is also VTH. So going back to the first equation, I had 2 times 100 times V2. And V2, I solved for a minus 400 over 201 times V1, which is now 0.027. And so this gives me a value of approximately a minus 10.6. So this is my VTH value. So now I want to find a value for RTH. So RTH is let me go through the first step, which is to remove the independent sources. So I'm going to remove this 1 volt. It becomes a wire. So that becomes a wire. That's because, again, V is equal to 0, looks like a wire. Again, another voltage, that's going to become a wire. And then I leave in my dependent sources. So I have one here, and I leave those in. I'm then going to apply a test source here. I'm choosing a voltage because it will then give me the exact current through this 100 ohm very easily. I'm going to call it I-test. And now I can write a node voltage equation right there. So I have a minus I-test. And this current is 1 over 100, 1 because of the 1 volt that I put on. And then the current in this branch is a negative 2V2 equals 0. So I have I-test as an unknown and V2 is an unknown. And I'm going to go back and take V2. And remember, V2 is the voltage at the top node, which I call V2A, minus the voltage at this bottom node, which in this case is 1 volt. So this is going to be V2A minus 1. V2A is the unknown. And again, that's going to be the current here, which is the same going through that whole branch. So V2A is a minus 4V1 times 100. So this becomes minus 400 V1 minus 1. And now V1 is an unknown. So V1 is here. And I can do the same thing I did before. Vx, I can locate it here and do a node voltage there. So Vx over 10 is going to be this current. This current is minus 4V1. And this current is Vx over 30. And those are my summations. And V1 I'm going to rewrite again as a minus Vx over 30. And I can plug that back in to this variable. So Vx over 10 minus a minus becomes a 4Vx over 30 plus Vx over 30 equals 0. Combining all my Vx's, I see that the only way possible for this to be a true statement is for Vx to be 0. So therefore, Vx equals 0, which means that V1 has got to be 0, which means that V2A is 0, which means that this becomes a 0. And my I test now is going to be a 1 over 100 minus 2, and V2 now is just the minus 1, so a minus 1. And so I can combine these to get I test is 1 over 100 plus 200 over 100 to give me 201 over 100. So RTH is V test over I test, and V test is 1, and I test is this 201 over 100. So we get RTH is 100 over 201, or approximately 0.5 ohms. And we redraw the Thevenin with the RTH being combined to, or connected to the A node, and the VTH we found as minus 10.6 volts. So I'm going to write that in as minus 10.6 volts, and that is tied to the B location. And this is our Thevenin equivalent for this circuit.